Okay, we're going to continue on. This will be L3. This is page 1 of my notes. On L3, I started a cheat sheet earlier, which is not going to be these notes. Anyway, if we move on, let's go back to our PowerPoint screen here because it's got more information. Not all my chicken scratch necessarily, but it has everything we've got here, right? So we've got here m dot is the product of density times volumetric flow rate, which is the product of density times area times the average speed of the molecules flowing through it. And remember our friend, the specific volume. Specific volume is the reciprocal of density. So I could also take V dot divided by the specific volume. Everywhere I have density, I could use the reciprocal of specific volume because density and specific volume are the reciprocals of each other. And again, I can find the volumetric flow rate by the product of cross-sectional area of the conduit multiplied by the speed of the fluid flowing through it divided by the specific volume of the material flowing through it. Remember earlier, I said, if you look back at your cheat sheet, I said, have some way of knowing the difference between your total volume, your specific volume, and your speed. These are all three different quantities. You're going to need three different ways of knowing the difference because you see here, all three show up in the same equation. So know which one is which. Which one of these four versions of this equation do you need? I don't know. Depends on what's given to you, right? They're all valid. They all work. And also, if I'm dealing with a control volume, I probably want to know the rate at which energy is flowing into or out of my system. So if I know the energy per unit mass, and I multiply that by mass per unit time, my mass flow rate, my m dot. So here I've got mass per time times energy per mass. This gives me energy per time. So putting a dot above a variable tells me I'm dealing with the rate of that variable, the speed at which that variable is flowing through. Time allowing. I'm just going to go ahead and put my examples at the end of these lectures here. So I'm going to continue on with some basic theory, but I do have a couple of examples, very simple examples we can work probably at the end of lecture 4. But we're going to keep moving here, right? So example will come, I promise. Okay, so if we talk about, so we've talked about different kinds of energy, right? We talked about internal, kinetic, potential. We've mentioned heat and work. There is also energy of mass flowing through a system. Conservation of energy, that's the first law of thermodynamics, groups all of these together. Conservation of energy principle groups all of these together. Now, what that means for us then is, again, energy cannot be created nor destroyed. It can only change forms. It is a conserved quantity. We believe, to the best of our knowledge, that there's a set amount of energy in the universe, and we can't create or destroy it. All we can do is move it from one type of energy to another. This is kind of interesting, kind of a neat way of thinking about it. So what that means is if I look at the energy of my system, all it can do is change forms. So in a lot of times in a physics text, I know I just taught, I happen to have this last semester for me, I taught physics 1 first time in about 10 years. And in the textbook they were using always uses final and initial. And that's fine. And maybe you're used to that also, F and I for final and initial. In a thermodynamics text, a lot of times we'll use 1 and 2 to represent initial and final because then later on we're going to start dealing with cycles where we have multiple states, not just 1 and 2. We'll probably have 3, 4, maybe even 5 and 6, depending on how complex the cycle is. So final and initial doesn't always work for us later. So we'll use 1 and 2 a lot. I know, like I said, when I taught physics 1 this last semester, I had to break that habit with those guys to be consistent with their textbook. But for us here, we're going to use 2 to represent the final state, 1 to represent the initial state, and at least for now, until a bit later. So change in the energy of the system, final minus initial. Remember, we said just a few slides ago, the energy of my system can take 3 forms. It can take internal energy, kinetic energy, and potential energy. So the change in the energy of the system would be the change in those 3 energies, right? And this is assuming if M is constant, which is a fair assumption a lot of times. So if your mass is constant, the change in the energy of the system will be the change in these three types of energy: a change in your internal energy, your change in your kinetic energy, and your change in your potential energy. So the energy within my system can change these different forms. What causes that change? Well, I can add energy to my system or I can take energy away. Um, so in this case, in physics 1, we would have learned about the work, the application of a force over a distance, and that's going to typically cause a change in kinetic or potential energy. What we're going to learn here is it could also cause a change in internal energy. It could be, some of that energy could be emitted out as heat, et cetera, et cetera. So, and later on, we may also have mass coming into or out of the system. So there are three ways we talked about in a closed system that you can have heat and work crossing the boundary. If mass can cross the boundary, that's a third way that energy can cross the boundary. So these are the ways that energy can come into or go out of a system. The first law is an accounting of energy. We're going to add all the energy in, subtract all the energy out, and that's going to tell us something about the change, which is right here. Right? In minus out, in minus out equals change. This is a very simplified version of the first law of thermodynamics. Add the energies coming in, subtract the energies going out. That equals the change in the energy of the system, which then ends up being this really big, long, I've written on 2 lines because it's big to fit onto the slide here. But I'm going to write that out with you guys by hand. And the good news is, yeah, it's one long equation. Don't worry. We're not going to use all these terms on a regular basis. I'm going to stop share here. And let's kind of go back to the basics here. If I add the energy in, E in, I subtract the energy out, E minus E out, that's going to equal the change in the energy for my system. Now, the ways that energy can come into the system can be heat. I'm going to add all the ends. You can group them together, but I'm going to add all the ends first. So it could be heat in, it could be work in, I could have mass coming into the system. And all three of those are ways that energy can come into the system. So I'm going to add all the ends. I'm going to subtract all of these going out. So I could subtract the heat out, I can subtract the work out, and I can subtract the energy of the mass going out. Now, as long as the mass is constant, meaning I have as much mass coming in as I have going out, they may be at different energies, but if I have the same amount of mass coming in as out, the mass stays constant, and I can just factor that out of all the other types of energies that can change for my system. So the ways that energy can change for my system is I could have internal energy change. I could have a kinetic energy change, so that's V2 squared minus V1 squared, both over 2. And I could have a potential energy change. That is G times the change in elevation, Z2 minus Z1. So this is all the energies in, subtract all the energies out, equals all the energies in my system that can change. And again, don't worry. That's we're not going to use all these terms all the time. In fact, a common chapter 4 problem, throughout the semester, our goal is going to be look at your system and figure out which of these terms can I cross out, which of these terms are the only terms that are important or going to impact what I'm doing. So we're going to be able to cross a significant number of these terms out as we go along through a problem, right? So a common chapter 4 problem we might encounter. I'll stop sharing so you can see this a little bigger. So a common chapter 4 problem might be, so basically I've got like a piston cylinder with, I'm adding heat to it, and as a result, that piston is going to expand. That expansion means that boundary work is going out. And so what you end up having is that the heat in minus the boundary work going out ends up equaling then the change in internal energy, because it's not, this piston isn't changing its potential or kinetic energy, the system's expanding a little bit. But So that, again, you see, we go from this down to just these terms. And I'm probably looking for the heat. I've got another way of finding the boundary work. And after chapter 3, we're going to have tools for finding the U values. We're going to add to this as we go. But this is kind of a simple example. When I say in here on my PowerPoint slide, hey, don't worry, we're not going to use all these terms. I'm serious. How many, I always ask this question, right? If we look at this big long equation here and say, well, how many unknowns can I solve for out of this? Or a lot of times I'll ask, how many equations do you see, right, on this line right here? How many equations do you see? And it's not a trick question. Um, I've got somebody's calling my office. I've got one equal sign there, right? I've got one equal sign. That means I've only got, let's see if I can pause. So I only have one equation because I only have one equal sign. So how many unknowns can I solve for out of this equation? Well, I can only solve for one unknown out of this equation, which means all the things, part of our goal in this course is to learn how do I take this long, complex, fundamental equation and break it down specifically just to the problem that I have in front of me. And that's really kind of our goal in chapters 4 and 5. Exam 2 material for us is learning how do I go from the big, long, complex problem, complex equation, law in this case, to specifically what makes sense for my problem. And then go through and systematically say, okay, well, what am I looking for? What is known? What can I find? Well, I'm looking for this, but I don't know this and I don't know these. Okay, what can I use to find this? Well, I can basically calculate the work based on the force that's being done. Okay, that's a good way to do that. Okay, I can use property tables to find the U values. Okay, so what's left? Well, heat, that's the only thing left. All right, we'll solve for the heat. That's the whole problem. Okay, so at any rate, hopefully that helps. What else have I got here? I think that's what I've got in for lecture 3 here. It is. We're going to pick up lecture 4 from there. And I'm going to rest my voice a little bit so I don't lose it. You guys keep up the good work.